Hello everyone, this is John Everest and this is my third video on high dynamic range images for lighting analysis. I've previously just talked about, I've contrasted a high dynamic range image with a low dynamic range image, and I've also indicated some of the data we can extract from a high dynamic range image. Now what I want to look at is um, now I want to look at is how we can use the high dynamic range images to actually sort of build up new images that we never actually calculated in the first place. So don't worry, it'll make sense. Imagine if you have a room with two lights, light A and light B. You had a calculation grid to record the measured light levels. You do a calculation only with light A, you record that light contribution. You do a calculation with light B and you record that light calculation. It's very logical that you could actually just consolidate the light from each calculation grid into a new calculation grid to understand what the light contribution would be from both light fittings, and we can do that with lit images. So to give you an example, here's a classroom again I've been using, and I've rendered every single light fitting one at a time. So we now have the luminous data for every single light fitting in isolation. Okay, and all I have to do is literally just add all those light fittings up. So providing I don't move my camera, of course, I just add one pixel onto the other pixel, and we build it up, and then we start to understand what it would look like if all the light fittings are on. And trust me, I've tested it. That image is exactly the same, physically accurate, the same as if I just rendered it all at the same time. And why would it not be? And we can perform all the same analysis I showed you in previous videos, because the image data and format is identical. We just arrived in a slightly different way. We can do the same thing with the windows. We can render a window at a time, or we can render sections of windows at a time. I like doing it this way because then I can simulate, that's like a blind, isn't it, drawn, or that's like clerestory glazing. So we have a bit more flexibility to do that. I could do a section of a window, one window at a time. You know, basically you need to scope out what is it you are trying to analyze and what flexibility you're going to need. Obviously, the more data you generate, the harder it becomes to manage. The production of these images is lightning fast. You're going to get them in like 30 seconds. To ray trace off these kind of images, well, on my sort of machine here, it's going to take like at least half an hour, and that's not for a super high quality image, but you're going to just under a minute, under a minute, under a minute, so you can really ask those questions and you can optioneer without bottlenecking the project timeline. So I can obviously just add all those sections of window together, and here's the daylit space without the electric lighting. And obviously physically accurate, so we can make our sort of we can consider the risks and opportunities of this scene. And finally, we can consolidate our consolidated images, bring them together, and there's the scene, just exactly the same scene created in a different way. But yep, it's all physically accurate and it's all good. So that's how you can sort of use. So basically, we can simulate obviously switching profiles there. So we can choose to isolate if we do not want all the lights on or all portions of the windows visible. We can very quickly just sort of remove lit contributions from each windows as a binary on-off switch. On the next video, I'm going to show you how we can be a little more sophisticated in how we can mix these images together. So I will see you on the next video.